All right, everyone. Thanks for bearing with me here. So, one of the reasons why the American South is the world's third largest economy and the world's best positioned economy for future economic development is because we happen to have the world's best economic developers, the most intellectual capacity, the most future focused strategies, and we have all of this located within SEDC. So we love to do these webinars so that our members who are the world's best can all come together to discuss various issues. So, which is certainly what we are here to do today. So I want to welcome you to the groundwater availability as a site selection factor webinar. And we are so excited today to have this session led by our partners at ECS, who are also a signature investor of SEDC. SEDC doesn't move without our investors and definitely our signature investors. More importantly, this group is a really important partner to all of us in the American South and state association. So we thank ECS so much for all that you do, and we're really excited to welcome Thomas Nelson to the webcast today. So Thomas is a principal hydrologist with ECS who specializes in groundwater source development, well design, numerical groundwater modeling, and groundwater impact evaluations. He is based in Charlottesville in the great state of Virginia and has more than 15 years of experience working as an environmental consultant on hydrological projects throughout the United States. So thank you, Thomas. Welcome to the SEDC webinar, and the floor is yours.
Thanks, Matt. Okay, so first off, if I break into a coughing fit, I apologize. I'm at the tail end of a cold, and I think I'm mostly over it. So I'm hoping I'm going to avoid that, but just wanted to give fair warning. All right, so in talking with the SEDC folks, I was told that this is a pretty savvy audience when it comes to groundwater use and the benefits of it. So rather than devote the time of this presentation to talking about why using groundwater can be beneficial, what I've done is I've tailored it to talk about the methods that we use when we identify the details associated with installing a well, like siting locations and aquifer targets, and the methods that we use to install, test, and sample the wells. But I thought I'd start with just one slide here talking about, what are some of the groundwater uses for an industrial, commercial, and municipal situations and some of the benefits. So obviously groundwater can be used for potable use. And when we talk about municipal use, this is most common where we have municipalities in an area where there is good groundwater availability, and they're using this to meet their municipal needs. From an industrial side of things, we have industrial process water, cooling water, which is really common at data center sites. Data centers need to be cooled to cool down the server rooms. And so oftentimes they'll use evaporative cooling to do this. Raw material dilution mixing, emergency water supplies. And this is just a list of a few uses of groundwater. Now, the benefits of using groundwater, it can be a very reliable source, and reliable in the sense also that it has an independence from municipal systems. So you are in control of your own system, you're in control of how much water you use, and this can be a real benefit. It can be highly cost efficient, especially if you're using a large quantity of groundwater. So if you're a facility that's using 300 gallons a minute, that's obviously going to be very expensive if your source is municipal. But if you can get that from groundwater, it can be significantly cheaper. Groundwater is oftentimes of very high quality, especially when you compare it to surface water sources, and there can be a low environmental impact, and this is dependent on the location generally. So if you are in a situation where you need to develop a groundwater source, what's your first step? Where do you start? And the answer to that is really dependent on the geologic location. So I'm going to talk about really three types of geologic settings. And for fractured bedrock settings and karst aquifer settings, you generally start with what we refer to as a well siting evaluation. And this is in contrast to a coastal plain sediment aquifer setting, where you would start with a feasibility evaluation. So there's some similarities to these different types of evaluations, but there are a few important distinctions as well. Now, regardless of your setting, there's going to be some common methods, which is that after you perform these initial evaluations, the next step is going to be well installation, followed by well testing and well sampling. And so that's really what the talk today is focused on, is going through these different steps that you would undertake if you were developing a groundwater source. So the first type of geologic settings I'm going to talk about are fractured bedrock and karst aquifer systems. Now, in a fractured bedrock aquifer, what you typically have, and it's shown in this diagram in the bottom left corner, is you have a zone of weathered rock, which depending on your locations may be 100 feet thick, it may be non-existent, but here where I am in Charlottesville, Virginia, our area, it's usually about 40 feet thick. And so this is oftentimes kind of a clayey, silty clay residual material, and this overlies the bedrock. Now, groundwater flow within the bedrock, because the rock itself has essentially no porosity, no permeability, the groundwater flows within fractures in the rock. And these fractures can be bedding planes, they can be fractures from expansion of the rock, but that's where the water moves. And so when you install a fractured bedrock aquifer well, what you're trying to do is installing it at a location where you intersect these fractures. Because if you install it in an area that doesn't have the fractures, again, you're just not going to have water being contributed to your well. So another type of setting is a karst aquifer setting. Now, karst is comprised of limestone. And when you think of karst systems, we're talking about areas like where you would see sinkholes or caves. And so what happens is you have these natural fractures in the rock, and the acidity of the rainwater interacts with the carbonate within limestone to cause dissolution. And those fractures that may have been a millimeter thick to start with can become inches thick or feet thick, or, you know, in some cases, obviously, caves can be hundreds of feet wide. And so what ends up happening is groundwater flows within these sometimes very large caverns or fractures and conduits, and you can have very rapid movement of groundwater, and you can have high volumes of flow within these types of aquifers. And because of that, whereas a well in a fractured bedrock system, you might have a 20-gallon-a-minute well, and it might be a great well for your location. In a karst system, you can get wells that have yields in excess of 3, 4, 5,000 gallons a minute. And so very high yield potential, but associated with that comes higher costs. And this graphic here in the middle, it shows generally where your karst terrain is in the US. The blue areas are where limestone is present, and the red is where you have karst features, meaning those sinkholes and caverns and all the issues that come along with that. So you can see we have some karst terrain in Florida, Alabama, Georgia, South Carolina, and then in Virginia here, kind of by me in the Shenandoah Valley, we have karst terrain. So in these types of geologic settings, in the fractured bedrock and karst systems, the first thing we want to do is a well siting evaluation, because where you put your well is of utmost importance. And I think this figure here kind of shows that. Each of these blue dots is a well up by Dulles Airport in Northern Virginia. And the number associated with it is the well yield, how much the well can produce. So most of these wells are 10 gallons a minute, 4 gallons a minute, 1 gallon a minute. I see some that are up to about 25. But these 3 red ones, these are wells that we installed for a data center client where we did well siting. and we have yields of 440, 370, 370. So doing this kind of studying evaluation, it doesn't guarantee that you're going to get a 370 gallon per minute well, but it's a great way to increase your chances of getting a high yield. So the first step that we do as part of these evaluations is a literature review and a well inventory search. We want to review any available geologic and hydrogeologic publications. We want to identify permitting requirements, which in a fractured bedrock setting in Karst typically is not too extensive. We want to compile a GIS database. And so we're going to bring in things like digital elevation layers, site polygons, probably stream layers, all sorts of different data sources that can help us with our evaluation. And we want to identify potential contaminant threats, because unlike a coastal plain system where you might have 200 feet of clay that prevents contaminants from migrating, in a fractured bedrock and karst system, you can have contaminants migrate pretty rapidly into the aquifer. And so we want to identify those potential sources before we actually install the well. So ultimately, what we try to accomplish with the lit review and the well inventory search is to figure out, does this appear to meet the, does the geologic setting appear to meet the client's water demand and quality requirements? Are there going to be multiple wells that might be needed? Are there space constraints with respect to setback requirements? So these are all things that are good to know up front and that we take into account when we're citing the location of the well. So the next step is typically a fracture trace analysis. Now, when I talk about fracture traces, what these are straight line lineaments that are topographic expressions at the land surface. And what we try and do with this is we're essentially trying to identify fracture zones that are expressed superficially. And so these fractures in the rock, when they make it to the top of the rock and become exposed, you have preferential weathering that occurs. And because of that, you can get like a lineament feature that's a subdued expression of topography. And that's what we try and identify. And we do this using a couple different methods. You can use old stereo pairs of photographs, which is shown in this upper right photo. And kind of a more up-to-date method that we really like to use is high-resolution digital elevation data. And high-resolution digital elevation data is every year there's more and more availability. And we have pretty good luck most of the time finding things like LiDAR data, where you might have an elevation point that is taken every 1 meter in a grid-like pattern. So highly accurate. Now you can see this bottom left photo. This is a site we worked at in Virginia, where it's a karst situation. And this is a hillshade map that we created based on digital elevation LiDAR data. And it's such high resolution that if you look closely, you can actually see depressions. And these depressions are sinkholes. And you can see on the left-hand side, this is a stream valley. And so you can see right where the floodplain goes up against that karst rock. Now, after we do our fracture trace analysis, we create what's called a compass rose. And you can see it here on this center graphic, where we try and identify the predominant orientation of these fracture traces, which we then use when we do our electrical resistivity survey. So the next step is the electrical resistivity surveying, or ER surveying as we call it. And what we try and do is cross these ER survey lines across the fracture traces, because the fracture traces can be great places to site a well. So the the ER lines are usually about 1,000 to 1,400 feet long, and they go along and they put what seems like rebar stakes about every 15 feet into the ground, connect it with a cord, and send an electrical pulse through the system. And what that does is it measures the resistivity of the subsurface to electrical current. And so you can see here two ER profiles that we did. Most of the rock is this greenish color. We have this red blob here that's highly resistant. And then we have this blue area. And the blue area is what we call a low resistivity anomaly. And we see these low resistivity anomalies when we have water-filled fractures, since the water is it has a low resistivity to electrical current. So in this particular case, we sited our well at about station 720 meters, where there was a fracture trace. And that target location on the center map is what we have here labeled as primary target. So this is that same well installed at that location. And it ended up being a really nice well. Produced about 150 gallons a minute. It was for a state park. Now, the well siting evaluation, everything I talked about, the literature review, fracture trace, the ER surveying, typically costs about $25,000 to $30,000. And like I said, not a guarantee you're going to get a high yield well, but it really increases the chances of getting a higher yield, especially in areas where low yields are common. So the next type of geologic setting I'm going to talk about, which is very different from the fractured rock systems, is coastal plain aquifers. So in a coastal plain aquifer, you have layers of sand and gravel that are sandwiched between confining units that are comprised of clay, silty clay, materials that really don't allow groundwater to be transmitted through it, or at least not large quantities of groundwater. So you can see in this graphic in the bottom left, this is a pretty typical cross-section of a coastal plain system, where the dark grayish area to the far left, that represents crystalline rock. And the light layers represent aquifers, and the orange layers represent confining units. And so these layers, they thicken as you move in a direction toward the coast, and they outcrop at the far left where the coastal plain system meets the crystalline rock. And this is what we call the fall zone. And it's a really important area because it's where these aquifers are recharged. Because of the thick clay layers that are above them, water doesn't really get into the aquifers within the most of the coastal plain. The recharge occurs at the fall zone where the aquifers are outcropped. And it's for that reason that municipalities and states are very protective of their fall zone. Now, unlike in a fractured system, groundwater movement in the coastal plain is between sediment grains, kind of like what's shown up in this upper right figure. So it's moving between the sediment grains as opposed to in fractures within the rock. And because of that, the exact location where you drill a well isn't nearly as important as the target aquifer that you install your well within. So very different than like in fractured rock system, where the exact location is the most important part. Like the fractured rock evaluations, the first thing we do is a literature review and a well inventory search. These are oftentimes more extensive than what's required for a fractured rock system. And we really focus the evaluation on the yield potential of the aquifers and the water quality of the aquifers, because you have some unique water quality concerns in a coastal plain system that you don't necessarily have in a fractured rock system, salinity being the most common concern. So ultimately, what you're trying to do with your literature review is identify what aquifer can be most cost effectively targeted to meet the client's water quantity and quality demands. Because if you don't need to put in an 800-foot well and you can get away with a 200-foot well, that's going to save you a lot of money. So that's really what you're trying to identify. So the next step in a feasibility evaluation in the coastal plain is to review permitting requirements. This is really important because permitting requirements in coastal plain areas are often much more stringent than in fractured rock systems. So in a fractured rock system, you're going to need to have a permit typically to install the well. And this commonly consists of submitting a form, a couple $100 fee, and maybe someone from the health department will come look at the well's location. Contrast that with the coastal plain, where water withdrawal permitting is usually required. And these permit applications can be consist of numerous forms, a lot of detailed information. It can be over $10,000 to submit these packages. So it's just much more of a process. The reason for this is because when you have overpumping in the coastal plain, you have a variety of issues that can be caused, like groundwater level decline, saltwater intrusion, regional land subsidence that really aren't issues in the Piedmont area or further inland. So I have a couple maps here showing Virginia and South Carolina, but each state that I'm aware of in the South and Southeast has water withdrawal permitting requirements. And you can see how the areas where water withdrawal permitting is required coincides with the coastal plain. And that's the basis for determining whether or not water withdrawal permitting is required. So really the goal of this part of the evaluation is to identify permitting requirements and start to have conversations with regulatory agency staff to identify roadblocks in advance. The next step is going to be to develop preliminary well design and to come up with some budgetary drilling costs. So the preliminary well design, the complexity of this is going to depend on the needs of the client. It can be as simple as a narrative description, writing out some general well specs, or it can be a full graphical depiction of the well with detailed specifications and writing driller bid documents. It just depends on the situation. We also like to get, like I mentioned, the budgetary pricing from drillers so that the client knows in advance what sort of costs are going to be involved with this well installation. Because, like I said, these types of wells can be pretty expensive depending on the construction. So at the end of the well feasibility evaluation, we should have a good understanding of target aquifer, drilling permitting requirements, and have a preliminary well design. These feasibility evaluations, they typically cost about $10,000 to $15,000. And considering the cost of what these wells, it's definitely money that's well spent. All right, so after you do your feasibility or your siting evaluation, the next step is going to be to actually install the well. So I'm going to talk about well installation and some of the things that are unique to each of the three types of geologic settings that I mentioned. So the first type of setting I'm going to talk about is fractured bedrock aquifers. This is the least expensive type of setting to install a well, commonly $20,000 to $25,000 to install a well for a commercial industrial site. And a really simple but pretty representative schematic is here on the right. And it shows that what you do is you essentially drill a borehole through the weathered rock material. You place either steel or PVC pipe to keep that overburdened material from collapsing into the well. You grout that pipe, and then you drill an open borehole through the rock. Pretty simple. You install these wells using an air rotary drilling rig. Sometimes you add some foam additive. It's good to have a geologist there to log the well, document the construction, identify depths and yields of water bearing zones, because this information can be critically important when you're determining the potential yield of the well. And here's a couple photos of wells that are installed in fractured rock settings. We do drill rig. In this case, we use steel pipe, well cap, cement grout. Now, karst aquifer wells are, the construction is kind of similar to a fractured rock, but there are some unique challenges associated with karst wells. And because of these unique challenges, they're more expensive. So I would say here it's generally 25,000 to more than $1 million for a karst well. And the biggest determination is going to be how large of a well are you installing? We just did a well a few weeks back in the Shenandoah Valley of Virginia that when we tested it, we found out that that well could produce more than 5,000 gallons a minute. And the well itself was about $700,000 because we had to have very large casing. We had to have a specialized drilling rig called a dual rotary rig. We had to develop the well for a couple weeks. So you can get some really high costs, but if you're doing a 6 or 8 inch well, you only need a couple hundred gallons a minute. It's going to be much cheaper and it's going to be much closer to that 25,000 number. So I mentioned the dual rotary rig, which sometimes is necessary, but more commonly, this type of well is going to be installed using an air rotary drilling rig, oftentimes with foam additive to bring the cuttings, add that viscosity, bring the cuttings up to the surface, since you can have air lost into these large caverns. And I show in this bottom right photo, we did a camera survey of that well I mentioned in Shenandoah Valley, and it doesn't show up great, but this is at a depth of 145 feet, and this dark area is the upper part of a very large cavern that's about 3 or 4 feet, 3 or 4 feet thick. And so you see that in these karst aquifer systems. Now the construction of these wells is pretty similar to in fractured rock, where you're setting usually steel casing into bedrock, and sometimes through mud seams that can cause problems with the water quality. And then through the production zone of the well, you're drilling with open borehole. The last type of well I'm going to talk about is coastal plain wells. These are, well, for commercial or industrial wells in the coastal plain, they can be quite expensive. They can range from around 100,000 to a couple $1 million, depending on the well and the well's yield. These high costs are usually due to high well material costs, especially these days. Longer drilling times, it can take, whereas you can install a fractured rock well in a couple days, it can take 4 months to do a full coastal plain well. Increased well development time, permitting requirements. So the construction of a coastal plain well is very different from that of a fractured rock or a karst well. What you essentially do is you use a mud rotary drilling rig, and mud is the drilling fluid. And when I say mud, I don't mean mud like you would scoop up from a puddle after it rains, but this is bentonite that's added to water. So you get a viscous drilling fluid. And what that mud does is when you put it down the hole as you're drilling, the viscosity of it keeps the borehole open and stable so that those sands and those swelling clays don't expand into the hole and cause the hole to collapse. In addition, it adds the viscosity that you need to bring the cuttings up to the surface as you drill. So you start by drilling your borehole, and once your borehole is drilled to the correct depth, you install a well screen. And this is different from in fractured rock where you don't typically need screen. But this is a photo of the screen, and there's many different kinds. But generally, it's just a way to keep those sands from collapsing into the well while also allowing water to move into the well. So you install screen in the aquifer, and you install what's called filter pack on the outside of the screen, which is essentially a graded sand. And above that, you install blank casing with grout. And what you're trying to do there is allow water from your target aquifer to move into the well while keeping any water from other aquifers outside the well with that blank casing and with the grout. Now, the well design is much more complex for a coastal plain well compared to a fractured rock well. And you base the design on things like borehole geophysics and sieve analysis as you're drilling the well. So that preliminary well design is not what usually what the well ends up actually being. It's usually a pretty close representation, but things like finalizing your screen slot size, filter pack gradation, screen intervals, that's all going to be based on your observations during drilling. Okay, so at this point, we've installed our well. And at that point, you need to ask yourself, is this well worth testing? That's the big question, because you don't want to spend the money to do well testing if the well's not viable. So when you drill a well, at least in a fractured rock and karst system, the air that the drilling rig adds down into the well causes water to come up out of the well. And how much water comes out of the well is a function of what the well can produce. So in a well that's a high yielding well, you're going to have a lot more water coming out of it than a low yielding well. So and that's called an airlift yield. So you look at your airlift yield and determine if this well seems like a viable well for your development, and if it's going to be adequate to meet the full development needs, or if you might need some additional wells. So if you look at that and you determine that it is a viable well, the next step is going to be doing aquifer testing. Now we like to do a couple different types of well tests. These are a step drawdown test and a constant rate test. And there's several purposes for doing these tests. The first and oftentimes biggest question for a client is, what is this well's maximum long-term sustainable yield? How much water can the well produce? You can use the data to estimate pumping impacts to other on-site or off-site wells. You can calculate aquifer properties, identify boundary influences that impacts well performance and the well's yield, calculate well efficiency, identify preferential pump placement depth. So it's really useful when trying to determine how you can operate your well. Up in the right corner, this is an aquifer test setup that I did a couple of weeks ago up in West Virginia. So you have the well here. We have our different measuring devices, which I'll talk about in the next couple of slides. And then water's being discharged a couple hundred feet from the well. When we do these tests, essentially what we're doing is we're pumping the well and we're causing a water level decline. And we measure that water level decline. And based on that data, that is what allows us to calculate these purpose points that I talked about. So the two types of pumping tests. The first is a step test, and we do a step test before we do the constant rate test. The step test consists of pumping the well at increasingly higher pumping rates, which we call steps. So the way we like to do it is we perform 4 steps usually, with each step lasting 2 hours. And we go right from one step into the next. So I have a graphic here, or the upper right graphic. This particular test, we did 3 steps with each step lasting 3 hours. And the y-axis is the drawdown, and the x-axis is elapsed pumping time. So you can see with this first step, we did at 200 gallons a minute. We had really rapid drawdown at the start, which is very common. And then it starts to stabilize. After 3 hours, we increased the rate to 250 GPM, and we get the same type of response. And finally, for our last step, we increased it to 275 gallons a minute, and we had another increase in the drawdown. And so each one of these groundwater drawdowns, patterns, it looks like a step. The next type of test that we'll do after the step test is a constant rate test. Now, the rate we use for this is going to be dependent on our step testing results. And typically, we like to do this test at a rate that's very similar to the rate that we plan on using as an operational pumping rate. These tests, the duration varies. They're commonly 24, 48 hours, but they can be 3 days or longer. When we do these tests, we're pumping the well at a single pumping rate, and we're maintaining very closely that rate throughout the test. And then at the end of the test, we measure recovery, how the well recovers. And like I mentioned, during the testing, what we're measuring is groundwater levels in the pumping well and also any observation wells that might be present. So this photo at the bottom right, this is a pumping test we did a couple of months ago. And this is a very large well. So typically you don't have a 20-inch casing, but this is the well that was a 5,000 gallon a minute well. So we have very large discharge piping, everything's bigger. But what we have here is, you can see the black device. It's called a pressure transducer, and it allows us to automatically record groundwater levels in the well at a frequency of up to 4 readings a second. That's usually not required in pumping tests, but we have that capability. We also will record occasional manual groundwater level measurements with an electronic water level meter, which we have the yellow one and also the red one. Other components of a pumping test setup, you can't really see it, but over here you can see a little bit of blue. That's a flow meter. And as the water moves through that discharge piping, it causes an impeller in the flow meter to spin, and it reads out what the pumping rate is. And that, combined with a valve that's also in line, is what allows us to control the pumping rate. So if I'm doing a test at 300 gallons, a constant rate test at 300 gallons a minute, I can typically maintain that rate within 1 or half a gallon a minute based on those flow meter readings. And how closely you're able to maintain the pumping rate to your desired rate is really a big factor in how valuable your data is. The last step is going to be water quality sampling. So the parameters that we will have our water quality samples analyzed for is very much dependent on client specific needs. And it's also based on regulatory requirements. So if you're doing a public well, your state health department is going to have a list of parameters that you need to analyze that water for. But additionally, a client might have some interest in the water that goes beyond what the state requires. So it's very much dependent on the project specific needs. And these water quality samples will usually collect during the final hour of the constant rate test. Okay, so I'm finishing up here, and I'm going to end the presentation with a brief case study that we finished a couple months ago. This was a project in Urbanna, Virginia, and it was for the installation of a municipal well. And this is in the coastal plain. So the center graphic shows the location of Urbanna. It's on the Middlesex Peninsula along the Rappahannock River, about an hour or so from Richmond to the east. Now, the reason that we were doing this project was kind of interesting. Uh, the town has 500 residents that their municipal system provides water to, and they have two wells as part of their system. They have a water withdrawal permit that allows them to withdraw a combined volume of up to 400,000 gallons per day. One of their wells was installed, actually both, one of them was installed in 1963, but they both have the same problem, which is that the well screen and the filter pack, which is that sand on the outside of the screen, it doesn't just screen one aquifer, it extends up the well and screens multiple aquifers, which in Virginia is illegal. It wasn't when this was installed, but it is now. And so they're being required by the Department of Environmental Quality to replace their well, both of them. We started with one, and the next one's going to be in the next few years. But just to describe the situation a little more, this well graphic on the far right, you can see the well screen in this graphic. It stops at the top of that deep aquifer. That's what you want your wells to do, and that's how they should be constructed. But the wells that Urbanna was using, and one of which they're still using, that well screen and the filter pack, it extends up through that overlying clay and silt and into the overlying shallow aquifers. And the reason that that is now not allowed is because you cross connect those aquifers, and it allows water to be exchanged between the aquifers. Essentially, water from whichever aquifer has a higher pressure will migrate to the well with the lower pressure. And the reason that that can be problematic is you can have contamination present. You can have salinity that can migrate. And you can have just water chemistry issues that are caused by the mixing of water of two different chemistries. So that was the reason why we're performing this well replacement. So the first thing we did was we performed a feasibility evaluation. And as part of that evaluation, we got a lot of good information about their existing wells and about the hydrogeologic setting of the region. So this table, it shows the general hydrostratigraphy. We have a couple of aquifers, superficial aquifer, and the Yorktown Eastover aquifer that are directly overlie one another. And then we have some confining units, and sandwiched between the confining units, we have the Piney Point aquifer, the Aquia aquifer, and the Potomac aquifer. Now, these elevations are based on publication data, and they're very much estimated, because you can see here that the Piney Point aquifer has a thickness of 90 feet. In reality, the actual productive zone of this aquifer is about 10 feet thick, and it actually has a very low productivity. So if you install the well in the Piney Point at this location, trying to get 400 gallons a minute, you're going to get a fraction of that, but it's still going to be an expensive well, and that kind of speaks to why we do these evaluations in the first place. So in the end, we found that the well being replaced was 662 feet, and that the Potomac aquifer was going to be the only viable target that would meet the client's demand and water quality needs. We found the Potomac aquifer at this location is of great water quality, no salinity issues. And we had conversations with the Department of Environmental Quality, and we found that they would be allowed to do a minor modification to their water withdrawal permit, which in contrast to a major modification is a significant cost savings, much less effort required. We found out from DEQ that they were going to require the installation of an observation well. And we got budgetary costs from drillers, and we found that the total estimated cost for the well is going to be $750,000, which is right at what the project ended up being. So we coordinated with the local health department as well. We identified well setback requirements, which for this particular site, because of its geometry, was actually kind of a challenge to find a drilling spot that would work. And we created a preliminary well design that was fairly detailed, and we wrote a bid specification sheet that the town then used to obtain drilling bits. So the town ended up obtaining USDA funding, grant funding, and that took a year and a half. So there was a pretty long lag in this project. But we began site work in April of 2023, and the well was finished in August 2023. So again, that speaks to how long it can take to install these coastal plain, these larger coastal plain wells. We installed an observation well, we installed the production well. You can see the well in this center photo, PVC casing, which using the PVC significantly reduced the cost of the well. We use stainless steel well screen, which is in the bottom left. This is a camera survey of the well, and you can actually see, if you look close, the filter pack behind those slots in the well screen. And we use our sieve analysis and our geophysical borehole data to optimize the well screen and the filter pack gradation so that we would have as efficient of a well as possible. Because when you have wells that are producing hundreds of gallons a minute, having an efficient well can save tens of thousands of dollars in costs, power costs each year, and that's largely a function of the well's construction. Additionally, an efficient well, you can have less drawdown in the well, which when your pump placement is regulated by a regulatory agency can be extremely of critical importance. So again, we use the data that we collected from the geophysical borehole data, the sieve analysis, cuttings collection, and we finalized our well design. And again, ultimately in August is when we completed both of the wells. We performed aquifer testing in September of 2023. This is a schematic of the final as-built well design. So we have about 40 feet of screen in the well. We had to be creative with the grout so that we didn't exceed the strength limitations of the PVC compared to steel. But our test was performed. We did a 48-hour test, performed our test at 440 gallons a minute. We ended up having only 27 feet of drawdown over the course of that 2-day test. A specific capacity of 16.3 gallons a minute per foot, which is very good. And after we finished our test, the water level in the well recovered to 96.1% of the pre-test level after 1 day. Sampling confirmed that the water was of excellent quality, and the town was going to have to do very minimal treatment, which when you're a municipality and you're talking about treatment requirements for surface water versus groundwater, this is what you want to see, because the treatment costs can be very high with a municipal surface water source. We did projections based on this data, and we projected that after 100 days of continuous pumping without any recharge, the water level in the well would be at 198 feet, which represents 32 feet of drawdown. And the DEQ requires your pump to be set above the top of the aquifer, which means that the maximum allowable pump depth in our well is 613 feet. And so you can see we have a 400-foot separation between our estimated operational water level and the allowable pump depth. So it's pretty clear that the town could get the 440 gallons a minute that they need, and that this well could produce a significantly higher rate. Okay, so just to summarize, our recommendations are that before you start a groundwater supply project, you start with the feasibility evaluation or a well siting evaluation. To do that due diligence work, that's going to help you make informed decisions, and ultimately can help you save a lot of money in the long run. Project approach and your well yield potential varies quite a bit based on your geologic setting. Likewise, project costs are highly variable depending on geologic setting and well construction, and your yield is mainly a function of your yield that drives that. Permitting requirements, depending on your state and location, can be negligible or very strict, with the most strict requirements being the coastal plan. And pumping tests are highly recommended. You get a lot of useful information that can inform you about what your well can produce from a yield operational perspective. So I thank you all for listening in. If anyone has any questions, I'd be happy to answer them.
Thank you, Thomas, so much. A lot of weeds here. Great information, as always, from our team at ECS. So, yeah, we have a few minutes to go here. We would love some questions. If you'd like, you can pop those in the chat, or turn your camera on, or not, or just and shout them out to us. So, got a few minutes. Ask away here while we have Thomas. Well, Thomas, you know you did a good job when you covered everything there is to cover. So we thank you so much for your time here. And before we part, do you have any final words, my friend?
No, I was gonna say that might also mean I just confused everyone so much that they don't know where to start. But hopefully it's the former and not the latter. But uh, no, I don't think so. Again, I appreciate everyone taking the time. And if you do have a project that comes up that you could use, feel like you could use a hand with, don't hesitate to reach out. I'm based in Virginia, but I work across the country. Any given day, I might be working on projects in Florida, New York, Pennsylvania, Virginia. We go everywhere. So, if you feel like I can help you, I'd be happy to have a discussion about it.
Well, great stuff. Yes, please take a photo here of the slide. We'll make these available too. It will be on our website. So that will conclude this one. The next webinar opportunity that we have will be Friday, February 16th. This will be a food and bev session, how to stay top of mind for food and beverage projects, led by Scott Kupperman, who many of you know is a consultant in the food and beverage space, and also Mary Lessa Pegg of EDP&C in North Carolina. So that one's free as well. So you can go to the SEDC website and sign up for that one. And with that said, thank you so much for your time today. More importantly, thank you for all that you do. We will see you next time on the SEDC webcast/webinar. Thank you.